Hello students. Now in this video we are going to look for the Cayley's theorem. Now it's an important theorem of algebra, and what does it says is that every group is isomorphic to a group of permutations. Okay. Now that means what? I have to take a group, a random group G, and I have to take another group, let's say G bar, which is a group of all the permutations. What is a permutation? We know basically a permutation is some bijective function 1 1 and on 2 that comes in the definition of permutation, and it deals with 1 2 3 and such kind of numbers or different arrangements of such numbers. Okay, but basically it's a bijection 1 1 and on 2. So any group should be isomorphic to a group of permutations. So I have to show that there exists an isomorphism from G to G bar. Okay. So what I will do is I will start with let G be a group. I will define a function on it, and I will show that it is a permutation. So for any G belonging to G, I will define a function, let's say Tg, from G to G bar, sorry, G to G itself, defined by Tg of x is equals to G into x, where this x also belongs to G. This is how I will show it. Okay. So now my next target is to show that Tg is a permutation. Okay. Permutation, that means I have to show that it is 1 1 plus onto. Then once it has been become a permutation, I will collect it all such kind of permutations in a group called as G bar. That is, it will contain such kinds of TGs where G belongs to G's. Now see, this G is a group, that means it will have G1, G2, G3 and all such elements. So this basically G bar will have all the functions like TG1, TG2 and so on. Okay. So now my next target is to show that this collection of all such permutations is also a group. This I will show via a two-step verification test. Okay. And then once this TG has been found to be a permutation, this G bar has been become a group, my next target is to construct an isomorphism from this G to this G bar and show that that function phi, which will be from this G to G bar, is an isomorphism. Okay, this is what it says. So now we'll start what to be done. So what my first target is going to be is to show, or my first claim will be to show that Tg is a permutation. Permutation, that means it is 1 1 and onto, that is to be shown. Now Tg is defined from G to G by Tg of x is equals to G into x for all x belonging to G. Okay. So what I will do is to show that it is 1 1, I will take x1 and x2 belonging to G. Okay, and I will assume that Tg1 of x1, sorry, Tg of x1 is equals to Tg of x2, and my target is to show that x1 equal to x2. So what I will do is this implies gx1 is equals to gx2. Now see, g is also in G, x1, x2s are also in G. Okay, therefore this gx1, gx2, they all belong to G. Okay, and G is a group. So that means what? I can just use left cancellation law and I can write x1 equal to x2. Okay, left cancellation. So that means what I have got, that tg1 from tg of x1 is equals to tg of x2. I have got x1 equal to x2, therefore tg is 1 1. This is what I have got. Now my next target is to show that it is onto. Okay, so what I will do is I will take some y belonging to this G. Okay, now if I see this, y belongs to G, also G also belongs to G, therefore G inverse also belongs to G. Now G inverse also belongs to G, y also belongs to G, therefore I know G inverse y belongs to G. Okay, why? Because it's a group finally. So that means what I will do is I will just take Tg of G inverse y. What I will get is G into G inverse of y. Okay. By associativity, I will get G inverse of y. This is equal to E into y. Basically, it is equal to y. Okay. So what I have got for y belonging to G, I have got what? That there exists G inverse y belonging to G such that Tg of this G inverse y is equals to y. So that means what? Tg becomes onto, Tg is onto, and since it is 1 1 and onto, Tg is a bijection and it's basically a permutation. Okay. Now, since it is a permutation, what I will do is I will create a group. I will create a set G bar where all such permutations exist. Tg where G belongs to G. So basically, as I said, for G1, G2, G3, etc. belonging to this capital G, Tg1, Tg2, Tg3, etc. belongs to this G bar. So now my next target or next claim is to show that this G bar is a group under composition of function, because TGs are finally going to be a function. So G bar is going to be a group of functions. Okay. So now what I will do is, now my first target is to show that the identity function belongs there. So what I know, identity belongs to G, therefore TE is there. Okay. Now this TE of X is going to look like EX, and that means what? It is X finally. So TE becomes the identity, is the identity. Okay. And this TE belongs to G bar finally, because E belongs to G. Okay. So now next target is to show that for any some G and H belonging to G, TG and TH also belongs to G bar. Okay. So that means now what I have to show, that their composition TG dot th, this also belongs to G bar. This is what I have to show now. Okay. Because for X and Y belongs to G bar, I have to show that X into Y belongs to G bar. Okay. I'm going via two-step verification. So now I'll start with TG th of X, the composition of two functions TG and th. So it will look like TG of th of X. This is basically TG of th of X is hx, and Tg of something is G into that something. So Tg of X. That is what I can just do it like this, and I can just write that Gh of X. Okay. Now see, G and H belongs to G. Therefore G into H also belongs to G. Okay. Therefore TGH, this belongs to G bar. So that means what? The G bar is closed under composition of functions. Okay. Now about the inverse part, that is for X belonging to G, the X belonging to G bar, X inverse should also belong to G bar, this part. For that, what I will do is I'll just take some G belonging to G, therefore G inverse also belongs to G, because G is a group. What I will do is I will just do it as Tg into Tg inverse, and this, just by previous stuff, I know that it is equal to Tg inverse of X, that is, it is basically equal to Te of X. Okay. So that means what happens is this Tg inverse is the inverse of this Tg. Okay. That means what? Tg inverse belongs to G bar. Therefore what? All the conditions are being satisfied, therefore G bar is a group. Okay. Now what is my next target? Next target is to show that this G and G bar, they are isomorphic. That means what? I will construct a function phi from G to G bar. Okay. And show that that phi is a isomorphism. And this phi of G from G bar is given by phi of G is equals to Tg. Because see, this is a group of all functions. This is a group of all elements. Okay. So elements has to be mapped to a function. So here also an element has been mapped to a function. Okay. So my claim is to show that this is an isomorphism. So basically I have to show that it is 1 1 and on 2. So for that what I will do is, for that 1 1 part I will take G1 and G2 belonging to G. Therefore I will just assume phi of G1 is equals to phi of G2. Okay. Now for this phi of G1 and phi of G2, what I have got is Tg1 is equals to Tg2. That is basically Tg1 of x is equals to Tg2 of x. Okay. Now see, if whenever you write f is equals to g, it is same as f of x is equals to g of x. Okay. So now from here I know g1 of x is equals to g2 into x. Okay. Tg1 is g1 into x, Tg2 is g2 into x. Now what I will do is, since we are in a group, I can just use right cancellation law and write down g1 equal to g2. Okay. Right cancellation. So therefore what I get is phi is 1 1. Next what I will do is, I have to show that phi is onto. So phi is from basically g to g bar. So I'll take some element over here, I'll show that there exists some g over here. So I'll take for some function f belonging to g bar, I will just define that f is equals to some tg for g belonging to g. Cause see, all the elements in G bar looks like of the format Tg. Okay, Tg1, Tg2. So whatever function, random function I take f, it should look of this form. Okay. So now what will happen is, I know that phi of g is equals to Tg, and which is equal to f, and where this g belongs to g. Okay. So that means what has happened, for any f belonging to G bar, there exists a g belonging to g such that this is what happens. Okay. Therefore phi is onto. So that has been done. The last part is operation preserving. Now what I will do is, for this I have to show that phi of g1 g2 of x is equals to phi of g1 into of x into phi of g2 of x. Okay, basically phi of g1 into phi of g2 of x, that is going to be my target. So I'll just use the left hand side, I'll get phi of g1 g2 of x as, I know this as t of g1 g2 of x. This is basically g1 into g2 of x, that is basically tg1 of g2x, and tg1 of g2x is defined as tg2 of x, that is basically same as tg1, sorry, tg1 into tg2 of x. And what is tg1? It is phi of g1. And what is tg2? It is phi of g2 of x. Okay. So that means what? It becomes operation preserving. This is equal to the right hand side. Okay. Now since it is operation preserving, therefore it is an isomorphism. Now since it is an isomorphism from G to G bar, that means what? G and G bar has been isomorphic. So this is what the theorem says. Every group which is G is isomorphic to a group of permutations G bar. Okay.